Okay, so welcome back. This is Discrete Optimization, Mixed Integer Programming, Part 4, and this is going to be quite exciting. So what we're going to see today are some really beautiful mathematics with very interesting computational results. Okay, so we're going to talk about polyhedral cuts, okay, very different from the cuts that we've seen before. Talk about warehouse location and node covering. Okay, so this is the motivation. So we're going to talk about the convex hull, right? So this is the linear relaxations that we saw last time of one of very simple mixed integer program. Okay. Now in practice, what we are really interested in are these integer points that you see there. Okay. And one of the things that we're going to look at is the convex hull of this particular point that you see on the screen at this point. Okay, so this is 2D. Okay, this is a larger 2D example. Once again, this is the linear relaxation of a MIP. These are all the integer solutions that you see there. That's the real thing we are interested in, right? And this is the convex hull of these guys, the convex envelope. That means, you take all these points, and this is essentially the smallest convex set, which include all these points. Okay. So this is 3D, so this is a 3D linear relaxation. You see all the integer points inside, okay? Once again, you could take the convex hull, that's, this polyhedra that you see there, and that's the convex hull of all the integer points, okay? Now, why am I talking about this? Okay, so assume that you have this beautiful convex hull. You have this region, this polyhedra there, okay? What could you do? Okay, think about it. What could you do? Well, one of the things you could do is to say, oh, I'm going to use an LP here, optimize my objective function. And by now, you know that if you optimize this thing, you're going to hit a vertex, right? What is that vertex? It's going to be an integer solution. And that's going to be the optimal solution to your MIP. So if I had this convex hull, okay, I could use linear programming and I would get the optimal solution immediately. Isn't that beautiful, right? So, in a sense, this is what we are going to talk about. We are going to talk about these polyhedral cuts, which are essentially these facets of the convex hull. Okay? If we had all of them, we would just use linear programming and we would be very happy. Okay? Now, these cuts, okay, they are valid. Okay? They don't remove any solution. I took the convex envelope of all the integer points. I'm not removing any of them. They are all included, right? And then they are also as strong as possible, right? So, and if I have all of them, I could just use linear programming and I would find the optimal solution, using the linear program. Okay? So why are these, polyhedral cuts very interesting? Because they are exploiting the problem structure. In that sense, they are completely orthogonal to the syntactic cut that we saw in the last lecture, which were based on the tableau. Okay? So basically what we're going to do here is look at specific constraints or specific properties of the problem and then generate these polyhedral cuts. Okay? Now, they share, of course, the same spirit as the syntactic cut, right? So they are valid. They don't remove any solutions, okay? They are always valid. They are just strengthening the formulation of the MIP. They are also cutting. We want to generate those that are cutting the optimal solution of the linear relaxation, right? So such that, we actually, get closer and closer to the integer solution. Okay, and of course we don't need to generate all of them. We can generate enough such that we can actually solve the problem effectively. Okay, now in a particular context, an application may use many of them. It's like global constraints in constraint programming. You may look at very different classes of cut and generate these cuts. Okay, they will exploit different substructure of the application. Okay, so what is the facet of this convex hull? That's a critical thing that we'll have to actually define. And so what you're going to see is that the mathematics behind it is easy. Of course, what the whole creativity is going to be finding this facet and then proving this simple proof. Okay, so this simple technique. So to find a facet, what you need to do is essentially find n are finally independent solutions or point which satisfy the faceted equality. They have to be on that facet, these points. Okay, and so a final independence is a simple thing to show. What you need to do is that if you have a set of n points, they are going to be affinely independent. If when you extend it with one more coordinates and put a 1 for that coordinate for every one of them, then you can show that they are linearly independent. And of course, linearly independence, you know what this is. It's simply saying that if you have combinations of all these points using alpha 1, alpha n, okay, for these n points, and if that is equal to 0, then all these alphas have to be equal to 0. So in a sense, showing that a facet is that something, some inequality is a facet, is basically going to be trying to find these points and showing that they are finally independent. Okay? So let's look at a particular example that we saw before. Okay, so this is warehouse location. Remember, we had to open or close these warehouses. Okay, and once they are open, they can serve customers. The goal was to minimize the cost of opening these warehouses and then serving the customers. Okay, so we had this beautiful MIP model with a very strong relaxation here, which was basically using these very simple constraints, right? Simple inequalities, two variables, stating that you can only serve a customer C with a warehouse W if warehouse W is open. Warehouse W is open means XW is equal to 1, and then obviously what you need to have is YWC smaller or equal to the value of XW. That's what you see over here. Okay? So in a sense, what you can wonder is, are these inequalities facets of the convex hull? Okay? So these simple inequalities are the facets. And so what you need to do is you need to look at these constraints, okay, at equality instead of inequalities, and find endpoints, okay, such that they are, and find endpoints which are finally independent. Okay? So I'm going to cheat a little bit here. I'm going to assume that we have only one warehouse, okay? And then you can generate these points here which satisfy these constraints and inequality. Okay? And so what we are looking here is we are looking at warehouse W and we are looking at customer 1, right? And we are looking at these very simple constraints. And what you see in the endpoints is that we're going to assume that XW is 0. Okay? If XW is 0, then Y1W has to be YW1 has to be 0, and that's the first point that you see there. And all the other customers, we put them to 0 as well. Okay? So we satisfy that constraint and equality. Now when this guy is 1, okay, so when XW is 1, okay, so then to satisfy the constraints and equality, we have to serve the customers with that particular warehouse, and that's the second point that you see. And then the other points that you see them is simply saying, oh, but I can take these other customers and say that it's using that warehouse as well. It doesn't impact that constraint, but we can find different points now, and they're going to be finally independent. Of course, you can generalize that if you have many warehouses by finding the right values for these different warehouses. Okay, so putting a 1 for every one of them in every one of these points. Okay, well, to get essentially endpoints. Okay, so in a sense, this is the kind of ways you prove that something is a facet. You look for these points, okay, and you are trying to show that they satisfy the constraint and inequality, and they are independent of each other. Okay, so let me look at another example now, because this was kind of too easy, right? So the formulation that we had already some of the facet. So we're going to look at another problem where it's not so obvious. And this problem is called node packing. Okay, and the key idea is, once again, you have a graph, with a variety of vertices, and then you have edges between these vertices. And what you want to do is to find the largest number of nodes such that any two of them is not connected by an edge. Okay, so you want to pack as many, that's why it's called node packing, right? You want to pack as many vertices as you can, but they can't be connected by an edge. Okay, so this is a packing, this is a beautiful packing with one vertex. Okay, and of course, as soon as I take, vertex 1, I can't take anything else because they are all connected to it. Okay, so this is another packing which has two nodes. Okay, so it has nodes 4 and node 6. Okay, so these two guys are not connected with each other, and therefore this is a packing. Okay, now a question that you may ask is that, is there a better packing? Is there a packing where I can actually pack 3 nodes? Okay, so look at this graph and try to think, can you see this mapping with 3 nodes? Okay, so we're going to come back to that. Okay, but what we're going to first do is to look at node packing and see if we can express it as a MIP. Okay, and once again, it's always the same story, right? What are going to be the decision variables and what are going to be the constraints? Okay, so in this particular case, the decision variables are easy. We're going to decide if a particular node is actually inside the packing or not. Okay, so a particular vertex is inside the node. And then we'll have constraints for linking two nodes. And what we know is that if we take this node, any node which is adjacent to it, which means that there is an edge between them, cannot be inside the packing. So we'll put this linear inequality to tell the MIP that this node and that node, because they are linked by an edge, cannot be inside the packing at the same time. Okay, and this is the formulation that you see here. Okay, so you see that the x1 to x6 are basically are variables which are associated with every one of the vertices. Okay, they are basically telling you if that particular vertex is in the packing, and then you see these very simple inequalities that are basically telling you, node x1 and node x2 cannot be packed, at the same time because they are linked by an edge. And so essentially for every one of the edges, you have these simple inequalities. And obviously every one of these variables has to be 0 and 1. And the linear relaxation here is basically going to relax this by saying that they are between 0 and 1. Okay? So this is the linear relaxation of the problem. Okay? So when you look at this, you can say, oh, but what is the linear relaxation going to do? And what I told you last time is that the linear relaxation is going to be evil. It's never going to do what you want, right? It's always going to try to maximize in this particular case. You maximize the largest part of the packing here, okay? So it's going to try always to do better, okay? And in this particular case, okay, the linear relaxation, okay, is basically going to assign 1/2 to every one of the decision variables. And therefore, the value of the objective function is going to be 6 times 1/2, which is 3. So it's basically telling you that the maximum you will ever be able to do is to pack 3 nodes on this simple example, okay? But of course, this is terrible, right? So this is entirely fractional and in the worst fractional way, right? So can we do better than that, okay? So now we have to think, you look at these problems and you are asking yourself, is there any kind of properties of the solution that will strengthen my relaxation, okay? So we want to find, a property of the solution. So essentially a constraint, okay, which is going to satisfy by all the integer solution, okay? And this particular case, there is a very useful concept that we find everywhere in optimization, which is clicks, the concept of clicks, okay? So when you look at this thing here, okay, so you see this, you see basically 2 clicks, okay? And so when you see a click like that with 4 vertices, and all the vertices in a click are connected to all the other ones, how many vertices can you actually, select in a packing? Well, at most 1, because that part, if you select 1, it's connected to everything else. So you can basically now select any of the other vertices. Okay? So as soon as you find a click, you know exactly that you can select at most 1 of the vertices in that click. Okay? So what we're going to do is take the formulation and add all the click constraints that were present in the instances that we looked at. Okay, so this is, and so we're going to do actually better than that. We are going to look at the maximal click. And what is the maximum click? Is the largest click that we can find. Okay, so it's a click that essentially cannot be extended further. Okay, so when you see this click here, you could say, oh, but there is a click with 3 vertices. Okay, but that click can be extended. So we won't state that particular click. We're going to take the click with 4 vertices instead because it's larger and therefore it's more constraining. Okay, so we're going to take this maximal click for every one of these. Well, for every, collections of vertices, okay? So as soon as you have a maximal click, okay, let's say for node 1 to 5, you can state a constraint which says that at most one of these nodes can be selected inside in the solution, okay? So in this particular case, we said that the sum of x1 to x5 has to be smaller or equal to 1, okay? So now what we can show actually, we can show that actually a maximal click is a facet, okay? And if you want to actually know what the proof is doing is the kind of reasoning for finding all these finally independent points that you will have to do is to say, oh, but if I have a click like this, and if I have another vertex, okay, we know that since this click is going to be maximal, that it cannot be, there is at least one edge with one of these vertices that is not there, okay? So it's missing at least one edge with one of these vertices. And that's how you will be able to find this a finally independent point. Okay, so this is essentially the MIPNO with all these constraints. Okay, so we remove all the other ones because they were basically subsumed by the click constraints. Okay, so they were smaller than the click constraints. So the fact that x1 and x2 could not be assigned the same value here is subsumed by the fact that we know that there is a click between x1, x2, and x3, and therefore it's subsumed the other one. So we basically have all the click constraints here. Okay, and that's the new linear relaxations that we're going to use, okay? Now, once again, this linear relaxation is really clever. What is it going to do? Well, one of the things that it's going to notice, of course, is that x1 is all over the place. So if we give a value to x1, essentially, it's going to take, some value for every one of these constraints. So what it's going to do is basically ignore x1, put x1 to 0, and then once again, you will have a completely fractional value for all the other constraints, okay? So when you do this, what is the linear relaxation giving you? Is giving you 5 times 1/2, okay, which is what? Which is 2.5. So we know already that the best packing we will ever be able to do is 2. Okay, so that's essentially it's actually a strong relaxation in this particular case. Okay, but one of the things that you have to remember here, okay, is that we don't have the convexal of the node packing, solution points, right? Because this solution is trill fractional. So what that means is that these click constraints are not completely characterizing the problem. You will need other kinds of cuts, okay? And there are some beautiful cuts that you can generate as well for doing this. But this was just illustrating with some of the cuts, you improve the linear relaxation, nicely, but they are not necessarily capturing all the convexal. Okay, so let me talk a little bit about another example that we saw before. Okay, so this was graph coloring. Okay, so we saw that what we were looking for is how many colors do we need to actually color this map of Europe. Okay, well, a small subset of Europe. Okay, and so one of the things that we had is having this linear, this MIP representation where we would assign, decision variable 0, 1 variable for to decide whether a particular vertex V was assigned a color C. Okay, so when you look at this relaxation, what we had was the fact that the objective function had to be greater than all the possible colors. That every country had to be assigned to exactly one color, and that adjacent country could not be assigned to the same color. That's what we had. Okay. So this linear relaxation was actually pretty terrible. So the only thing that we had was we need at least 2 colors, okay, which is kind of obvious, right? So if 2 countries are adjacent, you need 2 colors, okay? So can we do better? Can we actually find, some new constraints that can actually strengthen this linear relaxation, okay? And so what we saw, what we just saw is the concept of click, right? So can you actually use that concept in this particular case as well. Okay, so let's look at this graph coloring problem in terms of the graph. Okay, so you see basically you have an edge between, you have basically a vertex for every one of the countries and then a link as soon as they are adjacent. And what you see now is that there are a bunch of clicks. So this is a click of size 3. This is a click of size 4. Okay, so you see that there are basically plenty of clicks there. And once again, once you have that, you can do some kind of reasoning about the number of colors that you need in a click. Okay, so if you have a click of size 3, okay, how many colors do you need? Well, all these vertices are adjacent to each other, so you need at least 3 colors. If you have 4, how many colors do you need? Okay, so in a sense, what you can do is add these click constraints, and these are some of the constraints that you can use. Okay, so here this is adding a 3 click, okay, and what this is basically telling you is that if you look at the value of these vertices that are in a click, and if you sum the value that they have to be greater or equal to 3. Why 3? Because we have color 0, we have color 1, we have color 2. That's the smallest thing we can have with 3 colors, and that's 3. Okay, if we have a 4th click, we can do exactly the same thing, but now it's 0, 1, 2, and 3, which is 6. So we are basically taking all these 4 vertices, okay, and we are basically saying that the sum of these colors that they have, okay, has to be at least 6. Okay, so we can put these constraints in there, once again click constraints, and we can see what the relaxation is going to do. In this particular case, what you can see is that for when you add these 3 click constraints, okay, the number of nodes become the optimal solution takes 9 nodes. To find the optimal solution, you need 9 nodes, and the proof of optimality requires 41 nodes. When you use these 4 clicks, okay, so you get 5 nodes, and you get for finding the optimal solution, and 9 nodes for proving optimality. Okay, so what is nice here is that you need at least 3, you basically can add these constraints, they strengthen the linear relaxation, they shorten the proof of optimality and finding the optimal solution. Okay, so this is basically giving you the concept of polyhedral cut. Okay, so the way to think about it is that you are looking at constraints, okay, that are actually going to tighten the relaxation by using the structure of your problem. Okay, you can show that they are facet of the convex hull. That's really the best thing you can do because these cuts are as strong as possible in a sense. If you had all of them, you would just use linear programming. Okay, so what we'll do next time is looking at more interesting ways of generating these polyhedral cuts, and we look at them for also the traveling salesman problem. Thank you.